Now let's look at one more example, an object with an initial upwards velocity. A ball is launched from the ground with a velocity of 24.5 meters per second upwards. What is the maximum height that the ball reaches? How long is the ball in the air? And what is the speed of the ball when it hits the ground? So this time, the ball starts at the ground with an upwards velocity. The question didn't explain how. We could imagine it was launched upwards and it started at ground level. But that's not important for projectile motion problems. We're just given the initial height and velocity. The ball starts out moving upwards, it reaches some maximum height, then it falls back down and hits the ground. So first, how do we find the maximum height of the ball? There is an important thing we need to remember about projectile motion. The vertical velocity, Vy, is 0 when the object is at its maximum height in the trajectory. At this point, the ball is reversing direction, so it's not moving up or down at that moment. With that information, we know the initial velocity, the velocity at the maximum height, and the acceleration. So which equation can we use to find the y position at the maximum height? The only one we can use with the information we have is this equation. For this part, we're treating the maximum height as the final position. So we plug in 0 meters per second for the final velocity, 24.5 meters per second for the initial velocity, negative 9.8 meters per second squared for the acceleration, and 0 meters for the initial position. We can simplify that and rearrange the equation to isolate the final position, and we get 30.6 meters, which is the y position of the ball at the maximum height, when the velocity is 0. We also could have rearranged the original equation, keeping everything as variables, and then plugged in the numbers. Next, we want to find how long the ball is in the air. So what's the final time when the ball comes back down and hits the ground? For this part, we can use the same equation that we used in the last examples. Now, we're going to say the final point is when the ball hits the ground. So we plug in 0 meters for the final position, 0 meters for the initial position, 24.5 meters per second for the initial velocity, and negative 9.8 meters per second squared for the acceleration. We can simplify this equation, and if we want, we can use the quadratic formula to solve for t. But if we assume that the value of t is not 0, then we can just divide everything by t. Then we can rearrange the equation, and we get 5 seconds for t, the time it takes the ball to reach the ground. Now let's answer the last part. What is the speed of the ball when it hits the ground? First, we'll solve this with the same equation that we used in the previous examples. We plug in 24.5 meters per second for the initial velocity, negative 9.8 meters per second squared for the acceleration, 0 meters for the final position, and 0 meters for the initial position. That gives us 24.5 meters per second for the final speed of the ball. But now that we know the final time when the ball hits the ground, we could also find the speed using this equation. We plug in 24.5 meters per second for the initial velocity, negative 9.8 meters per second squared for the acceleration, and 5 seconds for time. That gives us negative 24.5 meters per second for the final velocity, and the final speed is the absolute value of the velocity, so positive 24.5 meters per second. Notice that the final velocity is the same as the initial velocity, except the final velocity is negative. When an object in projectile motion has the same initial and final y position, it starts and ends at the same height, the trajectory is symmetric. The initial and final vertical velocities are the same, but in opposite directions. We'll explain this more in a minute, but this fact is something you'll be expected to know about projectile motion. So we could have just answered this part conceptually by knowing that the final speed is the same as the initial speed, because the ball starts and ends at the same height. Now let's take a closer look at this motion, where an object starts with an upwards velocity. Here's what the motion looks like. What's happening to the position over time? And what happens to the direction of the velocity? Here's snapshots of the position at half-second intervals. Since the ball is in 1D motion, its path on the way up overlaps the path on the way down. So let's split up the snapshots with the ball moving upwards on the left and falling back down on the right. Using the same equation as before, we can find the y position of the ball at each time point. And here's the position versus time graph for this motion. Again, this might look like a two-dimensional trajectory of an object moving through the air, but this is just a graph of the height over time. So the y position starts at 0 meters, then it increases as the ball moves upwards. The ball reaches a maximum height of 30.6 meters at 2.5 seconds. Then the y position decreases as the ball falls down, and it reaches 0 meters again at 5 seconds. Notice that the time at the maximum height is half of the total time. That's because this trajectory is symmetric. It takes 2.5 seconds to go up and 2.5 seconds to fall down. Also, notice that the y position is the same at equal times before and after the maximum height. Half a second before the maximum height, it's at 29.4 meters. And half a second after the maximum height, it's at 29.4 meters again on the way down. So that's the position. What's happening to the velocity? We can use the same equation as before to find the velocity at each time. Then we can graph the velocity. It starts out moving 24.5 meters per second upwards, which is positive. As the ball rises, it slows down because of gravity. So far, we've only seen objects falling down, but for the first half of this motion, the velocity is upwards and the acceleration is downwards. Gravity subtracts from the velocity each second, so the ball slows down. Eventually, the velocity reaches 0 when the ball is at the maximum height. After that point, the ball begins to fall down and the velocity reverses direction. On the way down, the acceleration acts in the same direction as the velocity, so it speeds up as it falls. The graph is a straight line that crosses the horizontal axis at one point. So if we're looking for the time when the ball is at the maximum height, we're just solving this equation for the time when the graph crosses the horizontal axis and the y velocity is 0. Now let's look at the velocity vectors. The velocity has the same magnitude when the ball is at the same height, but they're in opposite directions. If we line up the velocity vectors at each time point, we can see how they're changing. This sort of looks like the velocity versus time graph. It starts out pointing upwards. It decreases as the ball slows down. It's 0 at the maximum height. Then it reverses direction and increases as the ball falls. If we look at 1 second intervals, each velocity vector is the previous vector plus the acceleration. For example, the velocity vector at 0.5 seconds is 19.6 meters per second upwards. The change in velocity each second due to gravity is negative 9.8 meters per second. If we add these two vectors tip to tail, the resultant vector is 9.8 meters per second upwards, 19.6 minus 9.8. This is the velocity vector of the ball 1 second later. Again, the vector changes by negative 9.8 meters per second, so 1 second after that, the velocity is 0. We keep adding this downwards vector each second, so the velocity vector starts pointing down and gets longer. Here's all three graphs for this motion. The position starts at 0 meters, increases to its maximum height, then comes back down to 0 meters. The slope of the position graph is the velocity, so it starts with a positive slope, then the slope is 0 at the maximum height, when the velocity is 0, then the slope is negative on the way down. This velocity graph is a good way to see how gravity is actually affecting the motion. The slope of the velocity graph is the acceleration, and the slope is the same when the velocity is positive or negative. Gravity isn't acting differently when the ball is moving up or moving down. It just changes the velocity by negative 9.8 meters per second every second, regardless of the direction. This creates an interesting position graph. The ball moves in one direction, stops, and then moves backwards. But the velocity just keeps changing the same amount every second. So that's what projectile motion looks like for an object that starts with an upwards velocity. So that's it for this video. Thanks for watching, and I'll see you in the next one.